All right, for this last video in sections 12.3 and 12.4, we're going to look at problems 10, 11, and 12 on the worksheet. So problem 10 says, find a vector orthogonal to the plane that contains the vectors u, which is 1, 6, 2, and v, which is 0, negative 1, 3. Okay, so we have u and v in the plane that contains the vectors, and we know that the cross product of these two vectors is orthogonal to both u and v. So that implies that the cross product is orthogonal to the plane that contains the two vectors. And the cross product, u cross v, is, as we can see by computing this determinant, 20, negative 3, negative 1. So this is a vector that's orthogonal to the plane that contains the vectors u and v. And note that we can easily check that u cross v is orthogonal to both u and v by looking at these dot products of u and u cross v and v and u cross v. So u dot u cross v, well, that's going to be 20 times 1 is 20, and then negative 3 times 6 is negative 18, and negative 1 times 2 is negative 2. Yep, we get a 0 dot product, so u and u cross v are orthogonal. And likewise, v dot u cross v, well, that's 20 times 0 is 0, negative 3 times negative 1 is positive 3, and negative 1 times positive 3 is negative 3. That comes out to be 0 as well, so v and u cross v are orthogonal. All right, great. So now let's press on to question 11. It says, let theta denote the angle between A and B. What value of theta will maximize A dot B? How about the magnitude of A cross B? Okay, so starting with the dot product, we know that A dot B is the product of the magnitudes of A and B times the cosine of theta. Okay, so noting that cosine of theta is bounded between negative 1 and 1, if we multiply through by the product of the magnitudes of A and B, okay, and noting that in the middle here, we just have A dot B from this result up there, we find that A dot B is bounded below by the opposite of the product of the magnitudes of A and B, and it's bounded above by the product of the magnitudes of A and B. And so, when do we achieve this maximum value, which is the product of the magnitudes of A and B? Well, that's going to happen when the cosine achieves its maximum of 1, and that happens when theta is 0 degrees. And note that when theta is 0 degrees, the vectors A and B point in the same direction. Okay, so A dot B is a max when theta is 0 degrees, when the vectors have the same direction, and that maximum value is the product of the magnitudes of A and B. Right? Now, as you've already seen, when theta is 90 degrees, A dot B is 0 because the cosine of 90 degrees is 0. And there, right, the vectors are orthogonal. And now, in this scenario, when theta is 180 degrees, that's when the cosine achieves its minimum of negative 1. And so there, A dot B is a minimum, and the minimum value is the opposite of the magnitude, or the product of the magnitudes of A and B. Okay, so that does it for the dot product. So then how about the magnitude of the cross product? Well, we know that the magnitude of the cross product is the product of the magnitudes of A and B times the sine of theta, which we know is the area of the parallelogram formed by the vectors A and B. Okay, and so now, noting that the sine of theta is bounded below by 0 and above by 1 for theta, restricted to 0 to 180 degrees, right, because remember that's our restriction on the angle theta between any two vectors. This implies, if I multiply through by the product of the magnitudes of A and B, that the magnitude of A cross B is bounded below by 0 and above by the product of the magnitudes of A and B. All right, so when do we achieve this upper bound? That's going to happen when the sine achieves its upper bound of 1, and that happens when theta is 90 degrees. Okay, so note that when theta is 90 degrees, okay, the two vectors A and B are orthogonal, and the parallelogram formed by the two vectors, in this case, is a rectangle. And the area of that rectangle is just base times height, right? That's going to be the magnitude of A times the magnitude of B. And that's the largest the area of the parallelogram formed by these two vectors can be. All right, so when is the area a minimum? That's going to happen when the vectors A and B are parallel. So either they have the same direction or they have the opposite directions, right? So when theta is 0 degrees or 180 degrees, in both instances, sine is 0, right? This lower bound. And that's when the magnitude of the cross product is a minimum. Cool. All right, so now let's press on to the last question, 12. So this says, let A be cosine alpha I plus sine alpha j, and B equal cosine beta I plus sine beta j. Use the fact that A dot B is equal to the product of the magnitudes of A and B times the cosine of theta, where theta is the angle between A and B, to derive a well-known trigonometric identity. All right, so let's first draw the vectors A and B. So here is the vector A. So let's say a little bit more about what the vector A is. So in components, right, A is cosine alpha comma sine alpha. Okay, so this is the vector. If I place its tail at the origin, its tip will be at the point cos alpha sine alpha. Okay, so this vector here forms an angle of alpha radians or degrees with the positive x-axis. Okay, and the base of this triangle you see here will be cosine alpha, and the height is sine alpha. And noting here, right, that the magnitude of A is the root of the sum of the squares of the components. Cos squared plus sine squared is 1. Right, the magnitude, the length of this green arrow, is 1. Okay, now by very similar argument, if we look at the vector B, which is cos beta I plus sine beta j, well, it will form, right, an angle of beta with the positive x-axis, and it also has magnitude 1. All right, so note here, right, since both A and B have magnitude 1, if we place their tails at the origin, their tips will lie along the unit circle. Okay, so now let's go ahead and translate what this result on dot products tells us about this scenario. Okay, so what is A dot B? What's the left-hand side? Well, A dot B, just multiply I components. So that's going to be cos alpha cos beta plus the product of the J components, that's sine alpha sine beta. That will equal, well, the product of the magnitudes of A and B. Well, A and B both have magnitude 1, so that's just 1 times 1, times the cosine of theta. And now what's theta, the angle between A and B? Well, as we noted, right, A forms an angle of alpha with the positive x-axis, and B forms an angle of beta with the positive x-axis. So the angle between green and blue will be the difference in those two angles, right? So in other words, theta is alpha minus beta. So if you rewrite this, you get the result that cosine of alpha minus beta is equal to cos alpha cos beta plus sine alpha sine beta. And this is the well-known difference formula for cosine that you likely have seen in pre-calculus. All right, great. Well, that's going to do it for this question. Thanks so much.